In this lesson, we're going to learn to find the derivatives for a monomial function. Now, in case you don't know what a monomial is just a special function where you raise some value x to some random power n. Now, to make this clearer, let's actually start by drawing a graph of some monomials. Now, usually, we only allow n to be an integer. Now, these symbols over here always seem to scare me, so I like to write down what they mean. We're saying here that n is in the set of integers. Now, if we chose n to be any number we like, if x was equal to 1, then I hope you can just see that 1 to the power of anything is just always 1. Now, no matter which value of n you choose, whenever x is equal to 1, then y has to be equal to 1. This is because 1 to the power of anything is always 1. Now, in a similar way, if we choose x to be equal to 0, then 0 to the power of anything is always 0, except for 0, but we can forget about 0. And now if you actually tried substituting -1 into the monomial, the value is actually going to change depending on the power of n. Whenever n is an even number, then -1 to the power of an even number is always equal to 1. For example, -1 squared is just equal to 1. However, when you choose n to be an odd number, then -1 to the power of an odd number is always equal to -1. For example, -1 cubed is the same thing as -1. So the first case we'd be interested in is when n is equal to 1. In this case, we'd actually get a straight line, because it goes through these points. Now, in the case when n is equal to 2, you have the graph of a standard parabola, so you'd have a graph that looks something like this. Now, when n is equal to 3, we again have an odd function, so it's going to go down here, go here, and then it's going to come up here. Then the pattern would just continue. X to the 4 would look like this, x to the 5 would look like this, and so on. And now we're led to an interesting thought. How are we going to find the derivative of something general, like this? By now you should be able to roughly draw what a derivative looks like, but how are you actually going to predict the function that represents the derivative of m2, for example? One of the things that makes a derivative hard to find is that the slope on different parts of the curve are not always going to be the same. So let's start by talking about the obvious cases first. Let's imagine m0. What would a graph of m0 look like? So as we can see, m0 of x is the same thing as x to the power of 0, and the graph looks a little bit like this. Now the reason the graph looks like this is because anything to the power of 0 is always equal to 1. Now technically I should put an open circle here, because 0 to the power of 0 is actually undefined. From now on, if you'd like, you can refer to 0 to the power of 0 as the root of all evil, but I'm sure you'll see that in due time. Now, no matter what we eventually discover the derivative of x to the n to be, we should expect that when n equals 0, the derivative should just equal 0. This makes sense because if you imagine a skateboarder on the surface of this graph, their slope will always be 0 because they're always moving horizontally. Remember that a dash on the top of a function name indicates that it's been differentiated. Now let's think about the case of m1 as well. We already know that when n equals 1, we don't have to write the power on, so m1 is just the same thing as x. Now for this function, a skateboarder would never actually change their gradient. They'd always be going up at the exact same slope. Now if you remember correctly, y equals mx is just the graph of a straight line, and m would be its gradient. Since we can write x as 1 times x, that means that the gradient we're expecting should be just 1. And that means that we'd expect the derivative of m1x to just be 1 everywhere, because the slope is going to be 1 no matter what x value you choose. Now these two cases are easy enough, but what happens when we go to the next case, which is m2, the parabola? Now unlike the cases above, in this case over here, we'd actually expect the derivative to be different based on the actual x value. You can see that over here the slope is really negative, and over here the slope is 0. Then over here the slope gets really positive. So I'm not really sure what I expect the derivative of this to be, but I do expect it to actually depend on x in some way. Now by just using the definition of a derivative, it turns out that we can actually find the derivative of x to the n for any value of n all in one go. Now instead of starting with the general case, I'm going to start by showing you how to differentiate x to the power of 3. Once you know how to do that, you'll be armed with a general technique that you can use to find the derivative of basically any power you like. So as I said before, we want to differentiate m3 of x, or in other words we want to differentiate x cubed. We can actually do this reasonably straightforwardly just by using the definition of the derivative. Now, I'm not going to lie, but the first time I saw this, I was actually pretty scared of it. I mean, look at all these things. But if you watch the introduction to the derivative, then I hope it isn't actually so scary to you. Remember, the derivative just finds the gradient, and this over here in a sense is the change in y, and this at the bottom is just the change in x, and all we're doing is just taking the limit as change in x goes to 0. Now in this case, we know that m3 of x is the same thing as x cubed, so we could just replace it, but I'm not going to do it just yet. First I'm going to start by dealing with the elephant in the room. What exactly should I do with this m3 of x plus change in x? Now in this equation, we've replaced x for x plus change in x, and that means everywhere we see an x, we should also replace it for x plus change in x, so we just get this. I've written all the change in x's in a different color, just to help you distinguish between them. Now I'm going to simplify this a little bit, just to keep things tidy. So just remember that raising something to the power of 3 is the same thing as multiplying it by itself 3 times. Now I would like to expand this, but I'm going to do it in a very deliberate way, just to show you something that you can use to help you expand higher powers as well. Let's start by just taking an x from each bracket to give you x times x times x. Now for the next term, I'm going to take a change in x from the first bracket and then an x from the other two. Now as you can see, I have a change in x followed by 2 other x's. But it's also possible for me to have the change in x second or third. If I had the change in x second, I'd take an x from the first bracket, a change in x from the second, and then an x from the third. And finally, I can also take an x from the first two and then a change in x from the third. Now if you look carefully, you'll notice in this first row over here, I only have x's, and in the second row I have exactly 1 change in x. But it's also possible to take 2 change in x's and then to take an x, which I can do in the next term. If you look carefully, there are 2 other ways that I could also have 2 change in x's. I could have change in x, x, change in x, or I could have x, change in x, change in x. And now, the only possibility we haven't accounted for is the case where we have 3 changes in x. Now, sure, that's a lot of terms there, but I hope you also realize that a lot of them are repeated. Notice that this term over here is just x times x times x, and that's the same thing as x cubed. All 3 of these terms have 2 x's and 1 change in x, so it's the same thing as x squared change in x, and since there are 3 of them, we have 3x squared change in x. Now continuing down the list, I hope you notice that all 3 of these are just repeated as well. Now since we have 1 x and 2 changes in x, this is the same thing as x change in x squared, and since there are 3 of them, we have 3x change in x squared. And finally, this last term over here is just change in x times change in x times change in x, which is the same thing as change in x cubed. So now that we know what m3 of x plus change in x is, we're actually ready to substitute everything into this and simplify it. Now for starters, we know that m3 of x is just the same thing as x cubed, so let's swap those first. Now for this term over here, we showed that m3 of x plus change in x was the same thing as all of this, so I can go ahead and replace it as well. Now this doesn't look a lot simpler, but I hope you notice that this term and this term actually end up crossing out. Now, because we only have 1 term in the denominator, we can actually split this fraction up into 3 parts. So now we notice even more terms cross out. We notice that we can cross these 2 out, this crosses out with a squared, and then this cube becomes a 2. Okay, so now we've actually hit the important point here. So far, we've been completely ignoring this limit at the front. The derivative in this form over here is not actually so useful to us, because it looks like we're dividing 0 by 0. But by writing it out like this and then doing a little bit of algebra, we actually get it to this final form over here, and now we're not actually dividing by 0 at all. So if we want to take the limit as change in x goes to 0 in this expression, it's actually really easy. All we have to do is make change in x equal 0, so we just cross them out. So by looking at this, we now know that the derivative of x cubed is just 3x squared. That's great and all, but we want to do it in general. We want to do it for the power of n. To do that, you're going to have to look a little bit more carefully at the steps we've performed. First off, I want you to notice that these 2 terms over here don't play a part, so this term over here isn't really important. This term over here, however, seems to survive the whole process because this change in x crossed out with this change in x. But these 2 terms, when you put them in here, they eventually ended up disappearing, because over here we let change in x go to 0. So when we let change in x go to 0, these 2 just cross out, and we ended up with the final answer, which is 3x squared. So because these 2 terms over here don't end up being important, we're going to refer to them as higher order terms. So I'm going to go ahead and replace all of this for higher order terms, which we call HOTs. Now keep in mind that they appeared over here as well, so we should replace them there too. Now this term over here becomes this term, but then the hots get divided by change in x to give you these two terms. So I'm going to rewrite these two as hots divided by change in x. So as we saw, the higher order terms just end up disappearing in the limiting process, but this term survives and this ends up being the final derivative. So if we were to change this 3 to an n, only one thing is going to change in all these steps that we took, and that's the number of brackets we're going to have to expand when we get here. However, the only terms we really care about are the terms where we have no changes in x and exactly one change in x. If we have 2 or more changes in x, then they end up crossing out in the limiting process, and we don't actually have to worry about them at all. So therefore, to find the derivative in general, all we really need to do is to generalize this formula over here. Now, in order to do this, we're going to want to learn to expand higher powers than this 3 over here. And because this lesson's getting a little bit long, I'm going to do that in another video.